So we're going to talk generally about fields, and then we're going to specifically talk about gravitational fields. All right, fields. So first, fields. You know, I actually prefer to just call it a force field. Why? Because so in like movies and stuff, your mental picture of a force field is like an invisible wall that nothing can get through, right? In physics, though, a force field is sort of something else. So we'll write a little quick definition. And it's going to seem vague at first, but when we talk about specific types of field, it should make more sense. So it is an area where objects experience force. Yeah, that's vague. Now, I just want to remind you, there are 4 fundamental forces in the universe. Okay, and each type of force has its own field. Okay, and we're going to specifically talk about gravitational fields and electromagnetic fields. Okay, and there's also, if you remember, the strong and the weak nuclear force, which are important, but we're not going to study them. At least not this year. Okay, so we're mainly concerned with this. So when I say area where an object experiences a force, in the case of gravity, we're talking about the object being something with mass. Okay, so anything with mass will experience force if it's placed in a gravitational field. This is what we mean when we say experience a force. And then with the electromagnetic, anything that is either, well, electrically charged, okay, or magnetic will experience a force when put in either an electrical or a magnetic field. And in fact, these are related, hence electromagnetic, because a moving magnet in an electric field will experience a force, and a moving charged object in a magnetic field will experience a force. It's just not quite as obvious how that works as it is with, say, gravitational fields. All right, so let's start with this. Let's take a mass, and that mass could be like, say, the Earth. Okay, we're going to show how we define what a field looks like. So this is the Earth, we'll say, or any other like massive object. Could be the sun, could be the moon, doesn't matter. And then let's say that we take another object with mass. Okay, some other object with mass. We'll assume it's a smaller object. This could be you and I. This could be a moon. This could be anything, right? It could be a rubber ball, whatever. Okay. If you place this object with mass anywhere near this object, anywhere within this object's gravitational field, this object will experience a gravitational force proportional to how much mass it has. Okay, so what does that mean? What that means is there will be a pull, right? There'll be a pull on this object, and that pull will face towards the center of the planet. Okay, we're going to define that and name that. That is going to be called the force of little g, the force of gravity. Okay, now let's imagine that we take this little mass, right, and we put it anywhere in 3D space around this object. No matter where I place it, it will always be attracted towards the center of the Earth, right? So if I take this thing and, you know, I don't want it up there, and I put it over here, it's still going to experience a force, okay? It's just that that force will be flipped the other way, okay? So like this. So what we're going to do is we're going to use this to define what the field looks like, okay? So what we'll say is, if this is the Earth or this is some object, okay, some massive object, and this is a test mass, we'll call it a test mass. Test mass. What we're going to do is use the test mass to map the field. So no matter where I put that test mass, we're going to find that the gravitational field will supply a force that aims towards the center. Okay, so we're using arrows to map the gravitational field. Call this field mapping. All right, now this shouldn't come as too much of a surprise, right? You guys know the Earth is round. You know that no matter where you stand on the Earth, whether you're on the North Pole, the South Pole, the equator, okay, gravity always acts down from your perspective. If you were to like zoom out on the Earth, no matter where you stood on this ball, the force applied to you would be down. Now, this doesn't represent a force. This represents how a force would act if we were to put a mass in any position around the planet. Okay, so gravity is never repulsive. All right, so anything with mass will always be attracted to anything else with mass. All right, through gravity. Now just remember, this is not indicating a force itself. It's just saying which direction the force will aim when I put my mass somewhere in the field. So here's a second question for you. Let's say I take the mass and I put it here, okay? And then let's say I take it and I put it like, I don't know, here, let's just move some things around. Let's do it here, actually. So what this is meant to represent is the same object, but at two different places, A and B. What do you think the magnitude of FG would be, comparatively, like bigger or smaller, at A versus B? Where do you think the actual force of gravity would be larger on this object? At A, right? Closer to the planet. And this is absolutely true. The closer you are to the planet, the larger the actual force of gravity would be. So if we want to use vector arrows, and let's just change the color here to represent the actual force. That's not a nice color. I want this one. As you move away from the planet, the strength of the gravitational field weakens, right? It never goes away, though. So that's an interesting fact. Gravitational fields extend to infinite distances. So as you move away, yes, the force of gravity decreases, but it never drops to zero. So people will say something like, oh, when you're out in space, there's no gravity. No, that's not true. You can be weightless, and we'll study that in a bit, but it's not because there's no gravity, okay? Because you're falling, but we'll get there eventually. So let's talk about a few things here. First, how do we figure out how much force there's going to be here? How do we do that? How much force is there here? Question mark. Okay. How much force is there at the surface of this planet? Question mark. Well, we know this, right? Force is the product of mass times acceleration. Am I right? Correct. So at the surface of Earth, there is a downward acceleration, and we've done like little tests with this. If you drop something, it accelerates towards the center of the Earth at 9.8 meters per second squared. So if you want to know how much mass there is, or how much this force of gravity is, you take m and you multiply it by g. G is just acceleration at the surface of the Earth. So if you weigh like, or if you have, say, a 10 kilogram mass, and you put it at the surface of the Earth, you'll find that it has a downward force of 98, mental math is hard, 98 newtons on it, okay? Now, if I move far away from the Earth, okay, far away from it, that G value will decrease. So if I go out here and I want to know what FG is, it might be like 7. Who knows, right? Somewhere above the surface of Earth. If you go out far enough, that 9.8 drops to 7. So this same object then would have a gravitational force on it of only 70 newtons. But the interesting thing is, no matter how far away I went, it would never drop to 0. So if I were to graph this, and we could say that the gravitational field strength as we move away is kind of like this, right? It never gets to 0. It acts over infinite distances, but it never gets to 0, all right? So that's kind of an interesting thing. So let's write down then what we know about gravity, okay? Gravity. What do we know about it? Well, one thing is that it is a fundamental force of nature. Fundamental. Okay, it affects mass. It's the force field and the force that works on mass, okay? 3, it's always attractive. As far as we know, there is no such thing as negative gravity. And number 4, it is the weakest of the fundamental forces. By an order of something like 10 to the 20 times roughly weaker than the next weakest one, which is the weak nuclear force. All right, so now I want to talk about a consequence of gravity, and that's weight. All right. So let's say we have the surface of our planet here, and we put you on the surface of the planet, okay? You have some mass, all right? You have some mass. That's a way of measuring the amount of stuff in you, right? The amount of stuff in you. No matter where you go in the universe, the amount of mass that you have is the same, right? You don't change. You don't lose atoms. It's a way that we measure stuff, okay? Matter. It's a property of matter. You kind of have a circular argument. You might say, well, what's matter? You say it's something that takes up space and has mass, right? Kind of hard to describe, I guess. So mass is a property of anything that is matter. It's going to have mass. There are things out there that don't have mass, like photons, for instance, that are still a thing, but they're not the same thing as matter. Okay, they're different. So let's talk about what's going on with you here. So you're in Earth's gravitational field. Remember those lines pointing towards the center. And we've already discussed the fact that you're going to have this force of gravity acting on you. It's going to be equal to mg. And let's just make you 100 kilograms. I know that's pretty big, but let's just do it. You've got 9.8 meters per second squared, and that's aiming down. So you're going to have 980 newtons, right, aiming down. Now, what are we going to call that? Well, we're going to call that the force of gravity. So then someone might say, well, what's your weight? Well, your weight is actually going to point up. I'd be like, well, what does that mean? Well, like, what do you mean it points up? Yeah, that's right. The weight in this case is actually going to be the normal. I should be careful, actually. Should just be careful. This is actually your apparent weight, and I'll explain what I mean by that in just a second. Apparent weight. This is actually your real weight. This is your real weight, and it's negative. You're going to say, like, well, what do you mean? Like, how can weight be negative? That doesn't make sense. Well, weight points down, right? But if I put a scale underneath you, right? So like you're standing on a scale, and we were to read what it says on the scale, right? That would read 980 newtons. And weight is measured in newtons, right? It's your mass that's in kilograms. Weight is in newtons, okay? People interchange them oftentimes. They would say, I weigh 100 kilograms. That's fine, okay? But from a physics perspective, weight is in newtons, okay? And it's m times g. So your apparent weight is up. In this case, it's the normal force, and it's 980 newtons. Now, why do I say that? The reason I say that, I make a big deal and say apparent weight points up, and it's equal and opposite to gravity, at least in this scenario, is because there are situations where your apparent weight can change. Here's one example. Let's say you take your scale up to the top of a cliff, and we drop it. Okay? And you and the scale get dropped. And we touched on this before. We touched on it. At this point, okay, you are now accelerating downward, all right? And there's going to be no normal force. So what would this scale read? Well, it's going to read 0 newtons. It's going to read 0 newtons because you and the scale are both accelerating downward in Earth's gravitational field. When you hit the ground, okay, assuming the scale doesn't get broken, it will start reading 980 again once you stop falling, okay? So why is this important? Well, it's important, for a couple of reasons. The first thing is, yes, there's still a force of gravity on you absolutely right now, and it is exactly what we had here before. It's 980 newtons. So you still have a 980 newton weight. However, your apparent weight has dropped to 0. What a scale would read has dropped to 0, okay? Here's why. In this situation, the scale is providing a normal force, and that's what the scale is actually measuring. It's got a spring in it, right? And as that spring gets compressed, there's a mechanism that moves this up or down, and it's all calibrated. And this spring, however much it's getting compressed, well, that's equal to how much upward force it needs to push on you to make sure you don't like accelerate through the scale, and that's what it's reading. But in this case, there's no way for it to provide that force, right? So it's falling, you're falling, this spring is fully extended, right? Because everything's like going at the same velocity downward, the same acceleration downward, I should say. And this will actually read 0, okay? Now, are there some scenarios in between this where you're not standing still, you're not in free fall, but you're somewhere in between these two things? Can you think of a situation? What about in an elevator? What do you think is going to happen to you? You get into an elevator and you put a scale under you. You're going to have to just like use your imagination here and think about what it felt like last time you were in an elevator. And when that elevator went from standing still to, say, accelerating downward, not at G, because that would suck. A free fall elevator would not be fun for anyone. But the elevator does accelerate downward. Maybe. While the elevator is accelerating, and it accelerates to some velocity, then it holds that velocity after a while. So it's going to accelerate and then just hold that velocity. During the acceleration, do you feel like this scale will read higher than your normal weight, lower than your normal weight, or 0? Lower. It's going to read lower. Now here's why. Remember, apparent weight, call it FA, is just equal to whatever normal force the scale has to supply. If the elevator is sitting still, the normal force has to be equal and opposite to the force of gravity down. However, in order to get you moving, what the scale does is it drops the amount of normal force and lets gravity accelerate you down a little bit. Not at full acceleration due to gravity, but at some like smaller fraction of the acceleration due to gravity. During that time, the scale supplies less normal force, reads less, and you feel lighter, okay? And if you go to full free fall, you feel weightless. It's not that your mass has changed. It's not that anything about the Earth's gravitational field has changed. It's how you're interacting with it that has changed. And the opposite is true if you switch directions. If all of a sudden the scale needs to start accelerating you up, then the normal force has to get larger than what it normally would be, right, in order to get you to accelerate upward. Okay, you can feel this when an elevator starts to accelerate upwards. You can feel that push of the floor up on your body, and you feel heavier, and the scale would weigh heavier during that acceleration. Okay, and we're going to stop there. We'll get into the actual numbers of this next time.